Hey everybody. We're going to kind of wrap up the discussion of applications of derivatives with this look at this concept of indeterminate forms and this derivative trick you can use called L'Hôpital's rule. I know it's spelled like hospital, but the S is silent. Sometimes you see this written with an O with a little caret thing over top. It's just, this is the way you write this kind of a silent S following an O in French. Anyway, I'll call him L'Hôpital. So the idea is, well, we'll first talk about what an indeterminate form is. Okay, so an indeterminate form is something that we'll see when we have limits. When we take the limit at as x approaches a of f of x over g of x. If the numerator goes to 0 and the denominator goes to 0, we have the indeterminate form of type 0 over 0. And if both the numerator and denominator go to an infinity, either positive or negative, we have an indeterminate form of infinity over infinity. And so anytime we have this kind of an indeterminate form for our limits, we can use L'Hôpital's rule to evaluate this limit. Okay, so if this is L'Hôpital's rule, if your functions f and g are differentiable, and as long as g prime of x isn't equal to 0 near a, and if this limit of f of x over g of x as x approaches a takes an indeterminate form of either type 0 over 0 or infinity over infinity, then the limit of f of x over g of x as x approaches a is going to be the same as the limit of f prime of x over g prime of x. So as long as your limit gives you an indeterminate form of either of these types, you can take the derivative of the top and bottom and then take the limit, and you'll have the same limit. This is super helpful because this indeterminate form can disappear, and oftentimes you can evaluate it super easily. Of course, sometimes this limit doesn't exist, so if the limit doesn't exist, then the limit doesn't exist. And of course, you may have to use L'Hôpital's rule a second time. That will happen. Okay, take this example. The limit as x approaches 1 of natural log x over x minus 1. You can see that as the natural log of 1 is 0, and the x minus 1 is 0, so you get 0 over 0 as an indeterminate form. So we can use L'Hôpital's rule and say this is the same as the limit as x approaches 1 of the natural log of x, that's 1 over x, and x minus 1, the derivative of that is just 1, so I would write like divided by 1, but I don't need to divide by 1 because that doesn't do anything. So we can just plug in 1 now and we've evaluated it. The answer is 1. Isn't that nice? Here you can see the limit of e to the x over x squared as x goes to infinity. Well, you can see clearly that both of these go to infinity, so this takes the indeterminate form of infinity over infinity, and so we can use L'Hôpital's rule. So this is the limit as x goes to infinity of e to the x, that's the derivative of e to the x, and then 2x. But notice that this is still indeterminate form of infinity over infinity, so we're going to do this a second time. This is the limit as x goes to infinity of e to the x over 2, which is infinity, or is to say there is no limit. It increases unbounded. Okay, let's take a look at this. The limit of the natural log of x over the cubed root of x as x goes to infinity. Now clearly both of these are increasing functions, so this is going to be infinity over infinity. But as you may guess, things are going to change when you take L'Hôpital's rule. So this is the limit as x goes to infinity. I'm going to put the 1 over x here, and the derivative of this is, now remember, we're not using quotient rule here. It's just the derivative of the numerator over the derivative of the denominator. This is x to the negative, or let's just put x to the 1/3 in the denominator. So the derivative of x to the 1/3 is 1/3 x to the negative 2/3, which is actually that's going to be 3x down here, and then x to the 2/3 here, but that's x to the 2/3 over x. That's the limit as x goes to infinity of 1 over the cubed root of x, 3 cubed root of x. And this, clearly, this limit is 0 because you're dividing by a number that grows and grows and grows. So this limit is 0. Now here we have one. You can see that this limit, as x goes to 0, what we have up top is, well, the tangent at 0 is 0, and x is 0, so it'll be 0 minus 0 over 0. Okay, so this is this form, like 0 minus 0 over 0. This is definitely indeterminate. So we're going to just proceed to use L'Hopital's rule. So this is going to be the limit as x goes to 0. The derivative of the tangent of x is the secant squared of x minus 1. And then down below we have 3x squared. Now we might observe that up top, that numerator, secant squared x minus 1 is actually just the tangent squared. So this we can write as the limit as x goes to 0. Actually, you know what we can do is take the 1/3 out of this. 1/3, the limit as x goes to 0 of the tangent squared of x over x squared. Now, if the limit of this thing exists, then I'll say if the limit exists, then this is going to be 1/3 times the limit as x goes to 0 of just the tangent of x over x squared. So if the limit exists, then the limit of the tangent squared over x squared is just that limit squared. So what is that? Well, if you evaluate that at 0, you'll get 0 over 0. So it's another indeterminate form. So we're going to take this one more step. This is the limit as x goes to 0 of the derivative of tangent x is secant squared of x, and the derivative of x is just derivative of x is 1. Now, we can evaluate the secant of x at secant of 0. That's not 0, that's 1, because the cosine of 0 is 1. Secant is 1 over cosine. And so what we have is 1 over 1. So we get is 1/3 times 1 squared. So we have 1/3 for our limit. Wild, huh? Okay, let's take a look at this one. Let's see what's the limit as x approaches pi from the left. Oops, I shouldn't put a minus 1, it's just minus. Sorry, the limit as x approaches pi from the left of the sine of x over 1 minus cosine of x. So the issue here, if you were to plug in, really you want to always remember to start by just seeing, well, what if you evaluate it? What you get is the sine of pi, remember, that's 0, and if you evaluate pi, let's see, 1 minus the cosine of the cosine at pi, you actually get 1 minus minus 1. That's 0 over 2. That's not an indeterminate form. In fact, that's okay. So if you have an indeterminate form of 0 times infinity, you can actually rewrite that as one of the other indeterminate forms. For example, take the limit as x approaches. Okay, the limit as x approaches 0 from the right of x times natural log of x. Right, you can see if you plug in 0, or if the limit as x goes to 0, what you get is 0 times like negative infinity, sort of. But that's not something we can use. What we do is we just write this as the limit as x goes to 0 of ln x over 1 over x. Because multiplying by x is the same as dividing by 1 over x. And what we have now is that this is like a form negative infinity over, if you approach 0 from the right, that would be infinity. You can use L'Hopital's rule in this case. It's an indeterminate form of infinity over infinity. So using L'Hopital's rule, this is the limit as x goes to 0 from the right of this natural log of x. You have 1 over x, and 1 over x, the derivative of that is negative 1 over x squared, which, let's rewrite that limit as x goes to 0 from the right. We have 1 over x, then we have an x squared. Well, it'll be negative x squared over x, which is just, this is the limit as x goes to 0 of negative x, right? This is just 0. Okay, so if you have an indeterminate form of type infinity minus infinity, then you want to see if there's a way that you can convert this into a quotient. Because you can't use L'Hopital's rule directly, you have to figure out how to rewrite this thing. For example, if we take the limit of the secant of x minus the tangent of x as x goes to pi over 2 from the right, now the secant is 1 over the cosine of x, and the tangent is the sine of x over the cosine of x. So you can see, even though as x goes to pi over 2, right, the secant and the tangent are both going to infinities, but if you observe that the denominator of both of these fractions is cosine, and so you actually can get sine 1 minus the sine of x over the cosine of x. Now, so this actually is the limit as x goes to pi over 2 from the left of 1 minus the sine of x over the cosine of x. Now, the numerator is approaching 0, and the denominator is also approaching 0. So this is of type 0 over 0. We can use L'Hopital's rule here. So this is going to be the limit as x approaches pi over 2 from the left of the derivative of minus sine is minus cosine of x, and down below we have a minus sine of x. Now we can actually evaluate this because the numerator is going to 0 while the denominator is going to negative 1. This is 0. That's no problem at all. So if you get an indeterminate form that's like an exponential, 0 to the 0th power, infinity to the 0th power, or 1 to the infinity power, you can usually use either logarithms or exponential functions to rewrite this in terms of a fraction. So let's take a look. Okay, the limit as x is going to 0 from the right of 1 plus sine of 4x to the power of cotangent of x. Now this is the base is approaching 1, while the cotangent of x, if you recall the cotangent, this is going to go to, as x goes to 0, the cotangent is going to be approaching from the right, let's see, as it's going to be approaching a positive infinity. Okay, so this is an indeterminate form. What we're going to do is let's just call this thing y. And so the natural log of y is, when you take the natural log of this business, right, you can take that cotangent and bring it down. And remember, the cotangent is just the reciprocal of the tangent. So we can actually write this as the natural log of 1 plus the sine of 4x divided by the tangent of x. So what we're going to do is try to find the limit of the natural log of this thing, and then what we can do is we can reverse that at the end. So let's take the limit of as x goes to 0 from the right of the natural log of 1 plus the sine of 4x divided by the tangent of x. Now here, what we have is a form 0 over 0. The tangent of 0 is 0, and the sine of 4x is 0. So and the natural log. So natural log of 1 plus 0 is the natural log of 1, which is 0. Okay, so it's the indeterminate form 0 over 0. So we're going to use L'Hopital's rule. And so this is the limit as x goes to 0 from the right. What we have is 1 over the 1 plus the sine of 4x times the derivative of 1 plus sine of 4x. That's going to be 4 cosine of 4x. And the derivative of the tangent, remember, is the secant squared of x. Now we can actually evaluate this because the sine of 4x is still 0. So what we're going to get is 1, well, I'll write it out. It's 1 over 1 plus 0. That 0 is in the denominator. And the cosine of 0 is 1, so that's times 4. And the secant of 0 is also 1, so it's over 1. So this comes out to be 4. So what we're saying is the limit as x approaches 0 from the right of the natural log of y is 4. And so what we're going to raise both of these to the e to these powers, e to the what we can to reverse this thing. All right, we would say that the limit of as x goes to 0 from the right of y is going to be e to the power 4. That's how you undo that's the inverse function. Okay, so take this one. You can see right away the limit as x goes to 0. Well, x to the x, both of those are, this is a 0 to the power 0 form. So what we're going to use, say y is x to the x. So the natural log of y is going to be x times the natural log of x. Right? It's the or which is to say that this is the natural log of x to the x. You can take the x and the exponent, bring it down, x times natural log of x. Now this is not going to be indeterminate form. This would be of the form 0 times a negative infinity. So what we're going to actually do is write this as the natural log of x over 1 over x. That is something we can do. So this is, right, the limit as x goes to 0 from the right of the natural log of x over 1 over x. So sorry, this is not the same thing. This is the limit of the natural log of this function. We already found that this limit is equal to 0. We did that a couple examples ago. So this example, this was 0. So the limit as x goes to 0 of the natural log of y was 0. So the limit as x goes to 0 from the right of y should be e to the 0, which is 1. And that's the limit for the original thing we're trying to look at. So a little tricky, but the technique works. So that's how you handle the limits of indeterminate forms, a nice little application of derivatives. All right, that is it. Bye.